I want to start with a question that might sound a little strange. What do you picture when you hear the words quantum computing? Maybe your mind conjures up those iconic images. You know the ones, those gigantic shimmering structures, often called chandeliers or dilution refrigerators, hanging down from the ceiling in heavily controlled lab environments. They're intricate, beautiful, and frankly, they look like something straight out of a sci-fi movie. And right there, nestled deep within those layers of cryogenic cooling, are the heart of the system. The qubits, plunged to temperatures colder than deep space, barely a whisker away from absolute zero. That's the image many of us have, and for good reason. It represents one of the leading approaches in the race to build a practical quantum computer. Systems that rely on matter-based qubits, tiny particles with mass like electrons or individual atoms that need extreme isolation to maintain their fragile quantum states. Think IBM, think Google, think trapped ions. But what if I told you there's another path being forged? A path that, at first glance, seems almost counterintuitive, almost impossible, based on everything we thought we knew about quantum systems and how they interact. A path that uses light. In this video, we're going to explore this intriguing approach. It's a form of quantum compute with possibilities that could fundamentally change the game. Does it work exactly like the silicon chips powering our world today? Is this future of computing really here, right now? Those are huge questions, and honestly, I can't give you a definitive yes or no answer today. The field is too complex, too rapidly evolving, and frankly, I'm not the one building these things. But what we can do together is explore the ideas. We can delve into the physics, the engineering challenges, and the ingenious solutions being developed. And I promise you, these ideas are absolutely mind-bending. Quantum computing concepts are, well, they're intense. Let's be honest. There are brilliant people who have dedicated their entire careers, decades, to unraveling these mysteries, pushing the boundaries of physics and computation. I have absolutely no intention of trying to cover the entire landscape of quantum information science in one video. And let me be crystal clear. I am nowhere near an expert. My goal here, and my journey in learning about this, is simply to understand enough to get to where we want to go in this story, which is exploring this fascinating photonic approach. Just a quick note, PsiQuantum did not sponsor this video. They were incredibly generous with their time and did provide me with some reading material, which, let me tell you, required a lot of head-scratching, so I could try my best to understand their technology. Any errors you hear? Well, they're mine. As they say, that is how the bird flies. You learn by doing, and sometimes you stumble. I will absolutely try to minimize them, maybe, if I'm lucky, by applying some mental quantum error correction techniques as I go. So before we dive headfirst into the quantum weirdness, let's start by reviewing something we do know well. Something fundamental that underlies the technology you're probably using to watch this video right now. Let us take a look at a regular, classical digital computer. At its core, a classical digital computer is built on a very simple, yet incredibly powerful foundation. It stores information inside what we call a bit, and a bit can exist in one of only two states. Think of it like a light switch. It's either on or off. We represent these states as a 1 or a 0. Simple, right? Binary. Everything. The words you read, the images you see, the sounds you hear, is ultimately broken down and encoded into vast sequences of these ones and zeros. Now, how do we do anything with this information? How do we perform calculations, process data, or run complex software? We manipulate those bits using things called gates. Think of these gates as tiny logical machines. They receive one or more bits as input, apply a specific logical function, and produce an output bit or bits. They literally gate the flow of information based on rules. Let's look at a couple of basic examples. The simplest is a NOT gate. It's like a light switch flipper. If a 1 bit goes in, it flips it to a 0 bit. If a 0 bit goes in, it flips it to a 1 bit. It negates the input. Then there's the AND gate. This one takes in 2 input bits. Its rule is simple. It's only going to output a 1 bit if both input bits are 1s. In any other case, if one is 1 and the other is 0, or if both are 0, the output is a 0 bit. So a 1 bit and a 0 bit gets you a 0 bit. A 1 bit and a 1 bit gets you a 1 bit. It's like needing 2 keys to open a lock. You only succeed if you have both. There's a whole family of these gates: OR, NAND, NOR, and so on. They perform different logical operations. And here's a critical point for our later discussion. Some of these gates, like the AND or NAND gate, are what we call nonlinear. What does that mean in this context? It means their output isn't just a simple sum or average of the inputs. The inputs interact in a more complex way to determine the output. Think about that AND gate again. If you just added the values, when 1 plus 0 are 1, you might expect a 1 output, but you get a 0. Why? Because the 0-bit input interacted within the gate's mechanism, which, in silicon, involves the complex physics of transistors and electron flow, in such a way that it prevented the 1 from passing through as a 1 output. The 2 inputs influenced each other beyond a simple sum. This nonlinearity is absolutely fundamental. It helps give the classical computer its immense power. Without it, computers would be limited to performing only the most basic, linear operations: simple addition, subtraction. We couldn't build the complex logical rules, the decision-making processes, the intricate simulations, or the rich software applications that we rely on today. Nonlinear gates allow the computer to make choices, to branch, to create complex outputs based on interacting inputs. So, the classical computing process is essentially this. We encode our data into these simple bits, 1s and 0s. Then, we send these bits through incredibly complex combinations of these gates, arranged in structures called circuits. These circuits transform the bits according to the desired logical rules. Integrate billions or trillions of these transistors, acting as gates, onto a piece of silicon. The yada 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 part involves mind-boggling engineering, and boom, we've got ourselves everything from the tiny chip in your smartwatch to a beastly NVIDIA B200 processing massive AI models. It's all built on this foundation of bits, gates, and the power of nonlinearity derived from physical interactions. Now that we've firmly established the groundwork in classical computing, using that solid, familiar foundation, we can, with a little bit of care and perhaps a deep breath, step over into the strange and fascinating world of quantum computing. We talked about how classical computing bits can only exist in one of 2 definite states, 1 or 0. Like that light bulb, it's either definitively on or definitively off. All straightforward, predictable jazz. In quantum computing, the fundamental unit of information is different. We store information not in simple bits, but in physical objects called qubits. These qubits leverage the bizarre properties of quantum mechanics. Like classical bits, these qubits do have definite, quantized states that correspond to our classic binary values, 1 or 0. We often call these the basis states. Think of them as the poles of a sphere. But here's the famous mind-bending part. Qubits can also exist in an arbitrary superposition of these 1 and 0 states at the same time. They aren't just one or the other. They can be a combination of both, to varying degrees. Imagine that dim light bulb inside a box again. It's not just on or off. It's simultaneously some percentage on and some percentage off. Or perhaps a better analogy is a spinning coin in the air. Before it lands, it's neither definitively heads nor tails. It's in a state of being potentially both, with certain probabilities. Of course, the quantum part of all this weirdness is what happens when we try to look. If we measure the qubit, if we open the box to look at the bulb, or if the spinning coin finally lands, then the qubit's superposition state instantly collapses into one of the two definite basis states, either 1 or 0. It's like, as soon as you look at the dim bulb, it either snaps to fully bright, H1, or shuts completely off, H0, according to the probabilities determined by its superposition state before you measured it. Yes, it sounds profoundly weird and counterintuitive to our everyday experience, but that is precisely where the power and the mystery of quantum mechanics, and thus quantum computing, lies. Just like in classical computing, where we use gates to manipulate bits, we can apply special operations to these qubits. We call these operations, you guessed it, quantum gates. Some of these quantum gates are conceptually similar to the classical gates we talked about earlier. For example, the Pauli X gate. It's one of 3 fundamental Pauli gates, and it acts like the NOT gate in classical computing. If a qubit is in the 1 state, it flips it to 0. If it's in the 0 state, it flips it to 1. If it's in a superposition, it flips the amplitudes of the superposition. But then there are gates that do things exclusive to the quantum world, things that have no classical equivalent. For instance, the Hadamard gate, often called the H gate. If you apply a Hadamard gate to a qubit that's in a definite state, say 0, it transforms that qubit into an equal superposition between the 1 and 0 basis states. It takes certainty and turns it into perfect uncertainty, a 50-50 chance of being found in either state upon measurement. If we were to measure this qubit immediately after applying the Hadamard gate, it would have a 50% chance of collapsing into 0 and a 50% chance of collapsing into 1. This gate is essential for creating superposition, one of the key quantum resources. Another, incredibly important quantum gate, one we'll definitely need to talk about later, is the controlled NOT gate, or the KNOT gate. Note that this gate is more complex because it acts on 2 qubits, not just 1. It involves a control qubit and a target qubit. The rule is this: if the control qubit is in a specific state, often denoted as the Ket1 state in quantum notation, then it flips the state of the target qubit, from 1 to 0 or vice versa. If the control qubit is in the Ket0 state, the target qubit is left unchanged. Now, why is the KNOT gate so important? Because by successfully applying the CNOT gate, we have done something profound. We have linked together 2 previously independent qubits in a fundamental quantum way. This demonstrates and is necessary for achieving another distinctive and powerful phenomenon of quantum computing: entanglement. When 2 or more quantum systems are entangled, their fates become linked, no matter how far apart they are. Actions or measurements made on one system's state will instantly affect or reveal information about the other, CIs. So imagine applying a CNOT gate to 2 qubits. They become entangled. Now, if you measure the state of the control qubit and find it's in the 1 state, you instantly know, without measuring, that the target qubit must be in its flipped state relative to what it was originally. And if you measure the control and find it's 0, you know the target is in its original state. Their states are correlated in a way that cannot be explained by classical probability alone. This link persists even if the 2 entangled systems are separated by vast distances, a phenomenon that famously bothered even Einstein. And this entanglement is not just a scientific curiosity. It's a crucial resource for quantum computation. It allows for parallel processing in a way impossible classically, linking the computational space of multiple qubits. In fact, entanglement is absolutely necessary to implement many of the most economically useful and powerful quantum algorithms proposed so far, including the famously disruptive Shor's algorithm. You know, the one that, if run on a sufficiently large and stable quantum computer, could efficiently find the prime factors of very large numbers? That task is computationally intractable for even the best classical supercomputers when the numbers are large enough, which is why widely used public key encryption systems like RSA rely on its difficulty for their security. Shor's algorithm could potentially break that. Now, why would someone want that capability? Well, that's a whole other conversation about national security, digital trust, and the future of cryptography, but it highlights the potential power locked within entanglement and quantum algorithms. So here we have the fundamental quantum computing concept in a nutshell. We encode data into qubits, leveraging superposition and entanglement. We apply quantum operations, quantum gates, to these qubits to perform computations, manipulating their superpositions and entanglements. And then, at the very end of the calculation, we measure said qubits. This measurement collapses their states, and we retrieve the results of our computation, encoded in those final ones and zeros, albeit probabilistically based on the final quantum state. Okay, the concepts are out there. Superposition, entanglement, quantum gates. Mind-bending stuff. Now, how do we take these abstract ideas and turn them into a real working computer? How do we build these qubits and gates physically? Most companies and research groups pursuing quantum computing today are following what are called matter-based approaches. These systems use particles that have mass, things like individual electrons, atoms, or carefully engineered superconducting circuits, as their physical qubits. These are the systems that often require those imposing, super-cold chandeliers. For example, one prominent matter-based approach is called trapped ion quantum computing. This is almost exactly what it sounds like. Scientists confine and suspend individual atoms or ions, atoms with an electric charge, using electromagnetic forces, holding them in place like microscopic marbles held by invisible tweezers. These trapped ions act as the qubits, with their internal energy states representing the 0 and 1. To perform quantum gates and entangle them, these tiny trapped qubits are precisely manipulated with finely tuned lasers. It's like performing surgery with light on individual atoms. Other major players like IBM and Google rely on a different matter-based approach. They use qubits made from sets of superconducting electrical circuits, often incorporating components called Josephson junctions. These circuits need to be cooled to extremely low temperatures, close to absolute zero, to become superconducting, meaning electricity flows with no resistance. Rather than using lasers to manipulate these superconducting qubits, they use precisely controlled microwave pulses. Now, a key advantage of these matter-based qubits is precisely because they are made of particles with mass and electric charge. They can interact with one another quite readily. This inherent interactability makes it conceptually easier to apply multi-qubit quantum gates, like the Knot, and to create entanglement between them. You can directly influence one qubit based on the state of another, because they can feel each other electromagnetically or physically. However, at the same time, this strength is also their greatest weakness. These matter-based qubits, being susceptible to interactions, can also interact with their surrounding environment. Even the tiniest vibrations, stray electromagnetic fields, or temperature fluctuations can disturb their delicate quantum states. This interaction introduces random noise from things like cosmic rays hitting the equipment or simply residual thermal energy, which can alter the qubit's state over time and, critically, even cause them to decohere. Decoherence is a fundamental challenge. It means that the qubit or qubits lose their special quantum behavior, their superposition and entanglement, and collapse into a mixed, classical state, effectively losing the quantum information they were storing. Think of it like a perfectly tuned guitar string that goes immediately out of tune if anyone touches it, or even if the room temperature changes slightly. This is precisely why these matter-based systems need complicated, intense cooling systems, like those dilution refrigerators or ultra-high vacuum environments. It's about minimizing any potentially disruptive thermal and electrical noise, creating a pristine, isolated quantum space for the qubits to exist in. It's like putting that delicate guitar in a soundproof, temperature-controlled vault. Advances in this area of the industry have been significant, making it possible to keep the qubits isolated and coherent for longer periods in their protected, super-cold environments. The problem arises when we need to bring them out, in a sense, and manipulate them to perform quantum gates on them. The very act of applying a gate, like entanglement or flipping states, involves deliberate interaction. And this interaction can inadvertently introduce random noise that can cause errors in the computation. When such issues happen, and they will happen frequently, we rely on techniques collectively known as quantum error correction. These techniques are incredibly sophisticated and use redundancy, spreading the information of one logical qubit across multiple physical qubits to detect and correct errors, conceptually similar to how a CD player deals with scratches on the disk by using error correction codes. While the development of quantum error correction was a monumental theoretical and experimental breakthrough, it presents its own challenges. The process of error correction itself involves complex quantum operations and measurements, and ironically enough, these operations can also introduce even more errors. So while essential, quantum error correction in matter-based systems is not a simple, complete solution. It's a complex and resource-intensive dance to maintain the fragile quantum state. Considering the inherent delicacy of matter-based qubits and the significant engineering required just to keep them coherent, the approach that most quantum computing companies using these methods have taken has been pragmatic. Start small and grow up. The number of qubits required to run truly useful, complex quantum algorithms that can tackle problems currently intractable for supercomputers, like breaking RSA or performing large-scale molecular simulations, is generally estimated to be in the range of hundreds of thousands, or more likely, 1 million, possibly many more, when accounting for the physical qubits needed for error correction per logical qubit. As they scale up towards that daunting number, new and increasingly challenging engineering problems emerge in maintaining precise control over every single qubit simultaneously, managing the complex wiring and control signals, and minimizing errors across a massive integrated system. Google is often seen as a leader when it comes to demonstrating progress with superconducting qubits and scaling. Back in December 2024, as per the source text, they announced a significant demonstration with a 105-qubit chip called Willow. What was particularly exciting about their claim was the report of unexpectedly good error correction rates as the qubit number scaled up. This had been a major theoretical fear, that error rates would worsen dramatically with size. The error correction capabilities they demonstrated certainly seemed like a legitimate breakthrough in that specific context. It undeniably did something for their stock price, reportedly soaring 6% the day after the December announcement and triggering positive movement in various other quantum computing companies, highlighting the market's sensitivity to perceived progress in the field. However, even with such impressive strides, it's important to keep perspective. Google's previous chip had 72 qubits, and they've now demonstrated 105. While the pace of progress is indeed quickening, and it will continue to accelerate with intense research, jumping from 105 qubits to the potentially million-plus logical qubits needed for utility-scale fault-tolerant computation still feels like a very long journey. It's not just a linear scaling problem. There are integration challenges, crosstalk issues, and control complexities that will inevitably arise as they attempt to bring so many interconnected quantum systems together. It's like trying to coordinate not just 100 perfectly synchronized dancers, but 1 million of them, all while they're balancing on a tightrope in a hurricane. It's formidably difficult. Transition card, photons, now. Finally, we can start talking about the alternative path, the one being pursued by companies like PsiQuantum. The path less traveled, which uses photons, particles of light. Photons have some core characteristics that make them simultaneously appealing and challenging for quantum computing. First, they have no mass. They travel at the speed of light, and they are relatively easy to generate and detect individually with modern technology. Though, as we'll see, easy is a relative term when you need them to be perfect, because they have no mass and no electric charge. Photon-based qubits have the opposite primary situation compared to matter-based qubits when it comes to interaction. On one hand, this is fantastic. It means they do not easily interact with their surrounding environment. A photon zipping through an optical fiber or waveguide is much less likely to be disturbed by stray electric fields, temperature fluctuations, or vibrations compared to a trapped ion or superconducting circuit. Quantum information stored in a photon tends to stay there, undisturbed. This inherent isolation is a huge potential advantage. It dramatically lowers the risk of outside noise causing decoherence. It implies that a photonic quantum computer might be inherently more robust and potentially easier to scale to large numbers of qubits without the same level of environmental fragility seen in many matter-based systems. It even raises the tantalizing possibility that, in some configurations, parts of a photonic quantum computer might even run at room temperature, eliminating the need for those incredibly expensive and complex cryogenic cooling systems. Though, as mentioned in the original text, there is a caveat here we might touch on. Certain components, like the detectors, often do require cooling, but the qubits themselves might be more resilient. But here's the flip side. As the old saying goes, your greatest strengths are also your greatest weaknesses. Because photons do not easily interact with their environment, they also do not easily interact with each other. They quietly pass through one another like ships in the night, oblivious. Recall back to our discussion of classical computing and the crucial concept of nonlinearity. We saw that without nonlinear gates, like the A&D gate, derived from the strong interactions between electrons in transistors, we couldn't build complex logic. The same principle applies here. We can produce single-photon quantum gates, like a Poly-X or Hadamard, relatively easily using standard optical components that manipulate the photon's single-particle state. But if photons do not interact with each other, how do you build a gate that requires two photons to influence each other? How do you create entanglement between two photon qubits? You need interaction for that. And without interaction, you cannot produce those critical nonlinear two-qubit gates like the knot, which are essential for universal quantum computation and unleashing the full power of entanglement-based algorithms like Shor's. For this reason, for a long time, many theorists and researchers believed that a photonic-based quantum computer, while appealing in its robustness, was fundamentally impractical for universal computation because of this lack of photon-photon interaction. How could you build a computer if the fundamental building blocks, photons, refuse to interact to perform the necessary logical operations? Then came a pivotal moment. In 2001, an incredibly interesting and influential paper was published in the prestigious journal Nature by three researchers, Nil, Laflamme, and Milburn. This paper proposed a theoretical setup, now famously known as the KLM scheme. The KLM scheme showed that it was theoretically possible to do universal and efficient quantum computation using only single photons, as qubits, and readily available, well-understood linear optical elements like beam splitters, phase shifters, and mirrors. The crucial insight? You didn't need photons to naturally interact with each other directly. You could make it as if they do by using other resources and a clever trick involving measurement. Let me try my best to break this down, because it's ingenious. In the KLM scheme, you have the photons that carry the actual quantum information you want to compute with. These are your data qubits, represented by single photons. These data qubits are encoded with quantum information using one of two primary ways, or variations thereof. The first is using polarization. A photon can exist in a superposition of polarization states. Think of the direction its electric field oscillates, like a wave wiggling vertically and horizontally at the same time. When they pass through a polarizing filter, like the lenses in some sunglasses, that superposition state collapses, forcing the photon's polarization to align to a certain direction. So we can define a horizontally polarized photon as representing the zero basis state, and a vertically polarized photon as representing the one basis state. Honestly, this encoding makes a bit more sense when you comfortably imagine light as a wave, rather than just a particle. Luckily for us, light has both wave and particle properties. The other way, and the method more widely used in industry today, including by PsiQuantum, is called dual-rail encoding. Here, a photon's quantum information is encoded by having it take one of two different physical optical paths or waveguides. One physical path is designated to represent the zero basis state. The other physical path represents the one basis state. What about superposition? This implies that when the photon is in a superposition state of 0 and 1, it is, in a sense, traveling through both paths at the same time, with amplitudes for each possibility. Once we measure this dual-rail data qubit photon by checking which path it's on, it collapses into either path 0 or path 1, according to the probabilities of its superposition. Before measurement, so tada, there's your single-photon data qubit, encoded in polarization or path. Nothing inherently special about this part yet. We've known for a long time that it's possible to encode quantum information into single photons. Let's get on to the hard stuff. How do you do those crucial 2-qubit gates like the Qubits if the photons don't interact? How do you create entanglement? This is done with a nifty trick. To pull this trick off, the KLM scheme requires the introduction of a set of extra photons, called the ancilla photons. Think of these as helper photons, or resource photons. They don't carry the primary data you're computing on, but they play an absolutely crucial role in making the computation possible. They begin in a known quantum state and follow their own carefully designed light paths alongside the data photons. The core of the trick involves using a specially designed optical network built from those linear components like beam splitters and phase shifters. Within this network, the paths of the data qubits and the ancilla photons are carefully mixed together in a deliberate, complex way. This mixing creates one very large, very complex combined quantum superposition state that involves all the photons simultaneously, the data qubits and the ancillas. It's like shuffling multiple decks of cards together in a very specific, controlled sequence. Here's the truly clever part. After this mixing happens, we measure the ancilla photons. We don't measure the data qubits themselves at this stage, because we still need them for further computation. We measure the ancilla photons using special single-photon photodetectors placed in their paths. This seemingly simple act of measuring the ancilla photons has a profound effect. Because all the photons were mixed and in a large combined superposition, measuring the ancilla photons instantly collapses this whole big, intertwined superposition state. And here's the magic. Depending on the specific outcome detected in the ancilla photons, which paths they took, which detectors clicked, the remaining data qubits are forced into a specific post-measurement state. If the photodetectors observe a specific predetermined pattern of outcomes in the ancilla photons, then we know that a desired operation, like a quantum gate, specifically a nonlinear 2-qubit gate like a Qubit, has been successfully applied to the data qubits. It wasn't applied by a direct interaction between the data qubits themselves, but rather mediated by their interaction with the ancilla photons within the linear optical network, and conditioned on the measurement outcome of those ancilla photons. We can now use this particular set of data qubits, which have undergone the desired transformation, e.g., become entangled, for later quantum operations. However, and this is the major drawback of the basic KLM scheme, if the photodetectors do not detect that specific predetermined outcome in the ancilla photons, which happens most of the time, then this particular operation, the attempt at the C0 gate, has failed. The qubits are in an undesired state, and we must discard the whole system of photons and try again. That's the major nature of this process. It is probabilistic. At best, the KLM scheme might achieve a successful CNOT gate outcome around 25% of the time. For other gates, the success probability might be even lower. The KLM scheme, despite its probabilistic nature, was rightfully seen as a significant theoretical breakthrough in the photonic quantum computing world. It showed that you could get a nonlinear computational result, like a CNOT gate, from linear optical equipment, using photons that don't naturally interact, by introducing auxiliary resources, ancillas, and leveraging measurement. It cracked the fundamental barrier. But as the paper's authors themselves noted at the time of its writing, their direct gate-by-gate setup had no immediate practical applications. And indeed, even after researchers were subsequently able to experimentally realize probabilistic gates like a CNOT using KLM principles, using this method to build complex quantum circuits, like we do with classical circuits, seemed formidably difficult. The problem, as we just highlighted, is that the gates are probabilistic. Creating a quantum circuit out of these probabilistic gates implies chaining together many such operations. But you can quickly do the math. If a quantum algorithm requires a circuit with, say, just two sequential C0 gates, and a single C0 succeeds at best with a 25% probability, or 1/4, then the probability of both sequential gates succeeding is 1/4, 1/4, 1/16, or 6.25%. If your circuit needs 10 such gates, the probability drops to 1/4 to 10, which is about 1 in a million. For algorithms needing thousands or millions of gates, the probability of getting a successful run through a circuit built purely out of probabilistic gates becomes astronomically small, rendering it useless. Those odds are definitely not in your favor. This seemingly insurmountable challenge eventually triggered a profound philosophical shift in how to approach photonic quantum computing. Instead of trying to build big, hairy circuits composed of sequential probabilistic gates with increasingly lower overall success probabilities, researchers began to follow a different line of thinking centered around measurement-based computation. Okay, here goes nothing. This is where things get even more conceptually tricky, and I'll give you an extremely simplified and rough explanation based on my understanding. If you recall, the KLM scheme's ingenious trick relied on the act of measurement, on the ancilla photons to effectively perform quantum operations, the gates, on the data qubits. This idea is incredibly important and is the kernel of measurement-based quantum computing. It's almost like the measurement act itself isn't just about reading a result, it's an active ingredient in the computation, a tool to sculpt the quantum state. Think of the desired quantum state or computation as a complex sculpture hidden within a block of marble. The measurements are like the precise strikes of a chisel, chipping away pieces to reveal the final form. We can use this idea not just for single gates, but to do much larger, more sophisticated calculations. The approach shifts from build a circuit of gates to build a special entangled state, and then measure parts of it. First, we produce a series of small, standardized entangled bundles or structures of photons. These are often called cluster states or resource states. Think of these as the primitive building blocks or the raw material for our calculation. They are like prefabricated, small entangled structures, maybe a few photons linked together in a specific pattern. Resource states can take several forms, but the key is that they are standardized, allowing us to produce many of them en masse. Before starting the main calculation, PsiQuantum, for instance, has written about using a specific resource standard made of 6 photonic qubits entangled together, conceptually, in a ring formation. These 6 photons don't necessarily stay physically together forever. Rather, individual photons from one resource state might be routed to entangle with other photons from other resource states, based on the needs of the calculation. And how is this larger entanglement between resource states achieved? Via the act of measurement. Just like how, with the KLM scheme, the act of measuring the ancilla photons forced the data qubits into a desired state or entanglement, here, measurements on specific photons within or between these resource states are used to link them together, building a larger, complex, entangled network. Some of these linking attempts via measurement will inevitably fail, just like in the probabilistic gate approach. And this has to be accounted for and dealt with by the overall system, perhaps by having redundant resource states ready, or by using more ancilla photons to boost the linking success probability. But the core idea is that with a sequence of such measurements, we can effectively merge these small resource states together to create a huge, massive entanglement lattice or fusion network. And interestingly enough, unlike the speed of light travel of the photons themselves, the process of generating the resources, routing them, and performing the linking measurements doesn't have to be instantaneous. Photons are made, entangled, and measured at our own pace, dictated by the system's clock speed and throughput. Anyway, by carefully controlling the sequence and type of the measurements performed on specific photons within this growing entangled lattice, you effectively sculpt or assemble the final computational state. It's almost like sewing patches together with various interconnections to form a complex quilt, where the pattern of the seams, the measurements, determines the final structure, the computation. This final network or quilt embodies the calculation's desired output or the state you need for the next step. At the very end, you might perform a final set of measurements on designated output photons to get a classical type result, the ones and zeros corresponding to the answer. Or the final entangled state might be used for something else entirely that we won't talk about right now in case our brain truly explodes. Okay? Deep breath. I really hope I got that right, or at least captured the essence of it. If not, well, sorry for adding to the confusion. But the key takeaway is the shift. Computation isn't gates acting on qubits, it's measurement driving the transformation of a large entangled state. So the theoretical path exists. Use measurement on ancillary photons to facilitate effective interaction and build computation from entangled resource states using measurement. But turning that theory into a physical working machine involves overcoming some significant technical hurdles. One of the major challenges with getting this to work reliably has been producing single photons that are not just a photon, but are identical single photons. Not just identical in energy or color, but indistinguishable in all their quantum properties: polarization, frequency, temporal profile, spatial mode. This perfect indistinguishability is critical. Visual. Graphic of the Hong-Ou-Mandel effect. 2 identical photons entering a beam splitter and exiting together. We depend on a unique quantum phenomena called the Hong-Ou-Mandel effect, or HOMI effect, which can be observed with a very standard optical component called a beam splitter. You encountered beam splitters implicitly in the KLM discussion, as they are key to mixing light paths. A beam splitter is basically like a half-silvered mirror. Its job is to split an incoming beam of light. A 50-50 beam splitter means that under normal, classical circumstances, or with distinguishable quantum particles, half of the photons that hit the splitter from one side would be reflected back, and the other half would go straight through. If you send one photon in, there's a 50% chance it reflects and a 50% chance it transmits. But the Hom effect describes something fundamentally quantum and counterintuitive. When two indistinguishable photons hit a 50-50 beam splitter simultaneously, one entering each of the two input ports, then they always exit together through one of the two output ports. There is never an outcome where one photon goes one way and the other goes the other way. There is no splitting of the pairs, which is exactly what you might expect with classical physics or distinguishable particles. And this happens because of quantum destructive interference between the possibilities. The probabilities for the split outcomes, one photon goes left, one goes right, cancel each other out perfectly because the photons are identical. The only outcomes left are where both go left or both go right. It is precisely through harnessing this Hom effect and its reliance on indistinguishable photons that we achieve this crucial quantum entanglement and the effective interaction between photons needed for measurement-based computation. But actually producing streams of perfectly indistinguishable single photons on demand, consistently and efficiently, that is as challenging as it sounds. It's like trying to produce millions of perfectly identical snowflakes. Naturally, there's always going to be some variation. On the other side of the process, after we've sent our photons through the optical network and performed the critical ancilla measurements, we've got to actually detect these single photons. This is another piece of crucial technology. The technology for single photon detection has been around for a bit longer than reliable indistinguishable single photon sources, and it's more mature. The most reliable option for high performance, high efficiency single photon detection, particularly relevant for this type of system, is apparently the superconducting nanowire single photon detector, or SNSPD. SNSPDs are incredibly clever devices. They consist of an ultra-thin wire, nanoscale width, made of a superconducting material, cooled to cryogenic temperatures, with a very small electrical current, a supercurrent, constantly passing through it. Because it's superconducting, there's normally no resistance to this current. However, when a single photon of sufficient energy hits the wire at a certain spot, its energy is absorbed. This energy is enough to break apart the Cooper pairs, the electron pairs that carry the supercurrent, in that immediate area, creating a tiny region where superconductivity is momentarily destroyed. So, a little hotspot of resistance appears and grows very rapidly. This hotspot only lasts for a few nanoseconds before the area cools down and recovers its superconductivity. But for that brief moment, the appearance of resistance causes a very small, detectable voltage spike across the wire. External electronic circuitry can recognize and amplify this tiny spike and register it as a click, indicating that a single photon was detected at that location at that specific time. SNSPDs are extremely sensitive, capable of detecting over 90% of the photons that hit them in some cases. And, as mentioned, the industry is rather familiar with them. They are already used in various high-precision applications outside of quantum computing, such as LiDAR, light detection, and ranging used in autonomous vehicles and mapping, and satellite communication systems. While implementing them in a large-scale quantum computer adds significant engineering overhead, they need cooling, for example. The fundamental detection principle is reliable and seems to work fine as a component for companies like PsiQuantum. So, armed with the theory of measurement-based computation via KLM principles and the need for technologies like indistinguishable single-photon sources and efficient detectors, we can look at who is actually building this. PsiQuantum was founded in 2015 and has been relatively quiet, diligently pursuing the photonic quantum computer vision for nearly a decade. Their approach is about high-performance, utility-scale, fault-tolerant quantum computing built on integrated photonics. They recently published a significant paper in Nature, discussing a new, highly manufacturable platform they call Omega. The key here is that this platform leverages commercial silicon photonics manufacturing processes, specifically from a large established semiconductor foundry like Global Foundries. This is a crucial strategic choice, aiming to tap into the scalability and maturity of the existing silicon chip industry, rather than relying solely on bespoke lab setups. The Omega platform integrates all the components needed on a chip or set of chips, generating those identical single photons, guiding them, performing the optical mixing to entangle them, the fusing, moving them around the circuit using optical waveguides, performing the crucial measurements, and detecting the photons with minimal loss as they travel through the system. When I visited their office, it was full of complex-looking systems, strange glowing optical fibers, intricate pipework for cooling, presumably for the detectors, and racks of buzzing electronic equipment. I have absolutely no idea what each specific thing does down to the detail, and frankly, didn't want to ask too many questions that would reveal the depths of my non-expertise. But the visual impression is one of advanced engineering integrating complex, optical, cryogenic, and electronic systems. The startup is actively developing large quantum computing campuses in places like Illinois and Australia, with the explicit goal of providing utility-scale quantum compute capabilities, meaning systems large and powerful enough to tackle those commercially relevant, currently intractable problems to those regions. They are certainly not alone in the broader space of photonic quantum computing, though I think PsiQuantum is unique in its specific large-scale integrated silicon photonics implementation aimed at fault tolerance from the get-go. Over in Europe, for example, there's Quandela. They are also trying to build a full-stack photonic quantum computer with a stated goal of reaching 50 logical qubits, meaning qubits protected by error correction, by 2028, representing a significant intermediate milestone. On the academic front, arguably the most formidable Chinese effort appears to be the work centered around the Jiuzhang series of photon-based quantum computers built by the University of Science and Technology of China in Hefei. They have built 3 versions of the Jiuzhang system between 2020 and 2023, demonstrating increasing scale and complexity. The first version, Jiuzhang 1 in 2020, performed a very specific, non-universal task known as Gaussian boson sampling, GBS. GBS is not a general-purpose computation. It's essentially a complex probability distribution problem involving photons. It's often used as a kind of quantum benchmark or demonstration of quantum advantage for a specialized task. Jiuzhang 1 performed this GBS task in about 200 seconds. The remarkable comparison they made was that performing the same specific task to the same fidelity would take the world's fastest classical supercomputer at the time an estimated 2.5 billion years. That comparison, even for a non-universal task, gives you a sense of the potential power jump quantum systems offer for certain problems. Right now, GBS itself has little direct practical application beyond demonstrating quantum computational power and potentially exploring certain mathematical problems. But the subsequent 2 Jiuzhang versions have scaled up the GBS paradigm, pushing the boundaries of how many photons can be reliably generated, manipulated, and detected in such a complex interfering system, showing continued progress in the underlying photonic hardware capabilities. So, as I said right at the start of this video, based on everything I've learned and the current state of the field, I cannot sit here today and definitively assure you that the general-purpose, fault-tolerant, utility-scale quantum computer is here in a way that's immediately accessible and world-changing for most tasks. There are still significant hurdles to overcome. We can point to things to say that it is not here in that ultimate sense. For example, all our public key encryption, like RSA, appears to remain intact and secure against practical quantum attacks for now. And even companies like PsiQuantum, while ambitious, have explicitly stated that there is still more difficult work ahead to realize their vision. They are trying something genuinely new, pushing the boundaries of physics and engineering. And such path-breaking endeavors always encounter unforeseen issues and require intense effort. There is also the crucial, real question of what this type of compute is actually good for. Right now, the industry understanding is that quantum computing, even when fully realized, will not and cannot replace classical computers for most tasks. You won't be writing emails, browsing the web, or running spreadsheets on a quantum computer. They are fundamentally different types of machines, optimized for different types of problems. Quantum computers excel at things that involve manipulating complex probability distributions or searching vast solution spaces simultaneously, problems that classical computers struggle with exponentially. But they generally have limited memory capacity compared to classical systems, which right now remains an outstanding question for certain types of algorithms. So, running large language models like ChatGPT directly on current or near-future quantum computers is not in the picture right now, as these models are incredibly memory-intensive. Right now, that universe of tasks where quantum computers are expected to provide a significant advantage is still quite specific, though expanding with research. Cryptography-related problems, like breaking current methods or creating new quantum-resistant ones, certain types of complex simulation problems, like modeling molecules for drug discovery or materials science, and complex optimization problems, like logistics or financial modeling, weather prediction or climate modeling could potentially benefit from improved simulation capabilities. One of the key goals for companies like PsiQuantum, alongside building the hardware, is to eventually bring these quantum compute capabilities out there into the real world, making them accessible perhaps through cloud platforms. Their hope is to let developers, scientists, and researchers outside the core quantum physics field start to experiment, play with, and build on this new paradigm. It's often when new computational tools are put into the hands of creative people that truly novel and unexpected applications are discovered. I look forward immensely to seeing that day arrive, whatever the technology that achieves it. Learning about this stuff, particularly the photonic approach with its challenges and the ingenious measurement-based solution, has been a journey for me. It reinforces a few things. First, that some of the most significant breakthroughs come from challenging fundamental assumptions, like the idea that photons needed to directly interact to be useful for universal QC. The KLM paper is a testament to the power of theoretical physics and creative problem-solving. Second, that truly ambitious goals require incredible persistence and long-term vision, like PsiQuantum's decade-long pursuit of this difficult path. And finally, it reminds me that understanding complex new ideas is a process. It involves grappling with concepts that feel counterintuitive, building knowledge layer by layer, and being okay with not understanding everything perfectly at first. The potential for errors is always there, but the willingness to explore, to learn, and to try to grasp these difficult ideas is what moves things forward, both in science and, I think, in our own lives. Don't be intimidated by complexity. Approach it with curiosity and humility, like a fascinating puzzle waiting to be explored. So as we wrap up this exploration of photons and the quest for a different kind of quantum computer, I want to leave you with a couple of lingering questions, ones that I'm certainly pondering. What impossible problem are you fascinated by? The kind that seems completely intractable with today's tools. And where do you think this incredible journey, whether it's via photons, trapped ions, superconducting circuits, or something else entirely, could eventually lead us? Thank you so much for joining me on this deep dive into the world of photonic quantum computing. It's a complex topic, and I truly appreciate you spending your time here. If you found this exploration interesting, confusing, or maybe a little bit of both, please consider subscribing to the channel. We'll keep exploring, the frontiers of science and technology together. Until next time, stay curious.